Binary search tree. Binary search tree is a data structure that quickly allows us to maintain a sorted list of numbers. It is called a binary tree because each tree node has a maximum of 2 children. It is called a search tree because it can be used to search for the presence of a number in big O of log n time. These are the properties that separate a binary search tree from a regular binary tree. All nodes of left subtree are less than the root node. All nodes of right subtree are more than the root node. Both subtrees of each node are also BSTs. They have the above 2 properties. The binary tree on the right isn't a binary search tree because the right subtree of the node 3 contains a value smaller than it. There are 2 basic operations that you can perform on a binary search tree. Search operation. The algorithm depends on the property of BST that if each left subtree has values below root and each right subtree has values above the root. If the value is below the root, we can say for sure that the value is not in the right subtree. We need to only search in the left subtree, and if the value is above the root, we can say for sure that the value is not in the left subtree. We need to only search in the right subtree. Algorithm. It checks if the root is null, and if not, it compares the target number with the data in the current node. Depending on the comparison, it recursively searches either the left or right subtree. The function returns null if the target number is not found in the tree. Let us try to visualize this with a diagram. 4 is the number that we need to find. 4 is not found, so traverse through the left subtree of 8. 4 is not found, so traverse through the right subtree of 3. 4 is not found, so traverse through the left subtree of 6. 4 is found. If the value is found, we return the value so that it gets propagated in each recursion step as shown in the image below. If you might have noticed, we have called return search 4 times. When we return either the new node or null, the value gets returned again and again until search root returns the final result. If the value is not found, we eventually reach the left or right child of a leaf node which is null, and it gets propagated and returned. Insert operation. Inserting a value in the correct position is similar to searching because we try to maintain the rule that the left subtree is lesser than root and the right subtree is larger than root. We keep going to either right subtree or left subtree depending on the value, and when we reach a point left or right subtree is null, we put the new node there. Algorithm. If the current node is null, it creates a new node with the provided data. If the data is less than the current node's data, it recursively calls the function for the left subtree. If greater, it calls the function for the right subtree. The function returns the modified node after insertion. The algorithm isn't as simple as it looks. Let's try to visualize how we add a number to an existing BST. 4 is the number that we need to insert. 4 is less than 8, so transverse through the left child of 8. 4 is greater than 3, so transverse through the right child of 8. 4 is less than 6, so transverse through the left child of 6. This is the correct position to insert number 4. Insert 4 as a left child of 6. We have attached the node, but we still have to exit from the function without doing any damage to the rest of the tree. This is where the return node at the end comes in handy. In the case of null, the newly created node is returned and attached to the parent node. Otherwise, the same node is returned without any change as we go up until we return to the root. Now that as we move back up the tree, the other node connections aren't changed. Deletion operation. There are 3 cases for deleting a node from a binary search tree. Case 1. In the first case, the node to be deleted is the leaf node. In such a case, simply delete the node from the tree. 4 is to be deleted. Delete the node. Case 2. In the second case, the node to be deleted has a single child node. In such a case, follow the steps below. Replace that node with its child node. Remove the child node from its original position. 6 is to be deleted. Copy the value of its child to the node and delete the child. That's it. This is how the final tree looks like. Case 3. In the third case, the node to be deleted has 2 children. In such a case, follow the steps below. Get the in-order successor of that node. Replace the node with the in-order successor. Remove the in-order successor from its original position. In this example, 3 is to be deleted. Copy the value of the in-order successor, which is 4, to the node. Delete the in-order successor. Binary search tree complexities. Time complexity. In the best-case scenario, where the data is optimally structured, the search, insertion, and deletion operations exhibit logarithmic time complexity, specifically big O of log n. This indicates that the operations have efficient performance when the data is well-balanced or organized. In the average case scenario, considering a range of possible data distributions, the time complexity remains logarithmic, providing a reasonable expectation for the typical performance of these operations on average. Again, it is expressed as big O of log n. However, in the worst-case scenario, where the data is highly unbalanced or skewed, the time complexity of these operations becomes linear, denoted as big O of n. This signifies that the operations may become less efficient when the data is organized in a way that maximizes the height of the structure, leading to a linear increase in the number of comparisons or movements required. Here, n is the number of nodes in the tree. Space complexity. The space complexity for all the operations is big O of n. Binary search tree applications. In multi-level indexing in the database, for dynamic sorting, for managing virtual memory areas in Unix kernel,